Question number 14 says, an element and its isotope only differ in the number of what? So an element and its isotope only differs in the number of what? So this takes us to the concept of isotopy. Isotopy. So isotopy is that concept, a phenomenon whereby an element of the same type, atom of the same element, having the same atomic number but different mass number. They will have the same atomic number, but different mass number. So now this takes us to the concept, how come about the difference in the mass number? So that takes us to the calculation of a mass number itself. So your mass number is equal to your number of proton plus number of what? Neutron. So when your number of neutrons are not identical, atom of the same type, they have the same proton but they have different neutrons, then there will be a difference in the mass number, because mass number is simply equals to proton plus what? Plus neutron. Okay, so now isotopy is a phenomenon whereby an element or element, let me call it element, or an element have the same atomic number but different mass number. Okay, they have the same atomic number but different mass number. A typical example is carbon 12, e.g. carbon 12 and carbon 13. So you have this to be C, so this is 6 and this is 12. You have this to be C, this is 6 and this is 13. Okay, so your mass number is number of proton plus neutron. That's your mass number is. So for carbon 12, for instance, for carbon 12, this one has 6 proton plus 6 neutron, and this was give us 12. For 13, this one has 6 proton plus 7 neutron, and this gives us 13. Okay, so this is due to, so we can now agree, we can all now agree that why you have this isotopy is because of difference in what? Difference in the number of neutron. So this is due to the difference in the number of what? Number of neutron. Okay, that's where you have your isotopy. So number 15 now. The thermal expansion of a solid is an advantage in so this is under heat, and this is under expansivity, maybe linear expansivity, or the expansion can be linear, radial, and all of that. Okay, so the thermal expansion of a solid is an advantage in, so the option A says balance of a watch, balance wheel of a watch. That's very correct. So it's an advantage in that domain. We use it in that to balance the wheel of a watch. And then construction of a steel rail line. So expansion is equally occurring. You have in your rail lines, you'll notice that a gap is being left in between. you know, the rails. This is to accommodate expansion and contraction. So during the heat, when the temperature is very high, the rails tend to expand, and the space that is left in between is for those expansion. Because if we don't do that, then that's going to have, we are going to have what we call derailment or derailing. You understand? So, and that's going to be a disaster. And you know, so we have that one. So there's not a particularly advantage per se, you know, but we have the concept of expansions occur there. And then you have construction of type bridges too. For bridges, you know, we equally put space for expansion, because bridge would equally expand and contract or compress, expand during heat when the temperature is high, and compress during cold period. You understand? So you usually have a space in between to cater for those expansion when it wants to expand, because if we don't give it a space, then he's going to find a space by itself, and this is going to lead to a collapse. You understand? So, and that's why you usually have that bridge. You can go there and inspect any bridge close to you. You'll see that space there. Equally, the rail lines. So go there and you'll see space in between. And you see this is the space that Kenny was talking about. This space is for the expansion. Okay? So, like that. So the fitting of tires on wheels is expansion is equally, but this is not an advantage here. So here, the thermal expansion of solid is an advantage. The thermal expansion of a solid is an advantage in the balance wheel of a watch. Okay, so that's question number 15. Then question number 16 goes this way. 16 says the SI unit of moment of a force is what? The SI unit of moment of a force is what? So the first thing that we need to know there is, what is a moment? What is a moment? Moment is the product of a force and the perpendicular distance from that point to the point of action. So let's say you have a beam like this, and then you have a force that is F, and then let's say we have a fulcrum here, and let's say from here to here is called distance X. So the moment here is force times distance. Let me write it in full. Force times distance, perpendicular distance. So you have that force times x, which is Fx. Okay, so if x is distance, so the unit of SI unit of force is what? Is Newton. And the SI unit of distance is what? Is a meter. So the SI unit of moment is therefore equals to what? Newton meters. So SI unit of moment is what? Newton meters. All right. So now question number 17. Question number 17 says a block and tackle pulley arrangement has 6 pulleys, in which an effort of 50 Newton support a load of 200 Newton. Calculate the efficiency of the machine. This is a repetition of question number 11. We've solved these questions on that number. So because of the way Jamb is now here, and you have random questions, so you may have this luck. So you just refer, I'm just going to refer you to question number 11. It's the same question that was solved there. So refer to question number 11. Look at the solution under question number 11. It's the same as this. Okay, so question number 18. Question number 18 says, calculate the light of the image formed by a pinhole camera of length 12 centimeter used to photograph an object of 60 centimeter away from the hole and 70 centimeter high. So here this is under light. So we're given that the length of camera, so the length of camera is 12 centimeter, okay, and the object distance is 60 centimeter, okay, from the O, and 70 centimeter high. So object height is equals to 70 centimeter. So calculate the height of the image. So image height is not known. Image height is not known. So here, solution, magnification. Recall that your magnification under light is equals to the length of camera divided by the object distance this same magnification again, if I call it M, this same magnification is equals to the image height all over object height. Now, so I'm going to be using these tools for my solution. Now, so the length of camera is 12 and the object distance is 60. So I have my magnification M to be equals to 12 centimeter, because they are all in centimeters. So I can have all over object distance, which is 60 centimeter. Okay, so this is going to be 12 goes in 60 is I think 5 times. So this is 1 over 5. So 1 over 5 is 0.2. 5 goes in 1 is 0 point, and then in 10 2 times. So this is my magnification. So, and recall that your magnification is image height all over object height, which is equals to magnification is 0.2 is equals to image height I don't know, all over object height we have been given to be equals to 70 centimeter. So therefore my image height is equals to 0.2 times 70. So this is just you dividing 70 by 5. Okay, this is just you dividing 70 by 5. So this is equals to 14, or just 0 times 0, 0 cancels this 0, 2 times 7, 14 centimeters. So your image height is equals to 14 centimeters. Okay, so that's your question number 18. Then question number 19 says, when two objects P and Q are supplied with the same quantity of heat, the temperature change in P is observed to be twice that of Q. The mass of P is half that of Q. The ratio of the specific heat capacity of P to Q is what? the ratio of the specific capacity of P to Q is what? So you have there are two objects, P and Q. So let's say we have them to be this, P and Q. So you have the heat in heat supplied to each of them to be the same heat is supplied, so let's call H to be H. So the temperature change in P is observed to be twice that of Q. So if this one is T, if temperature is T, so the one in P is 2T, while this one is T. It's observed to be twice that of Q. And the mass of P is half of that of Q. So mass of P is half. So let's say the mass is 0.5 m and this one is m. So the ratio of the specific heat capacity of P to Q is what? So you remember, so they said C to specific capacity, ratio of specific capacity of P to Q is what? So that's what we're looking for now. Remember, your heat is equals to mcq. So recall, so specific heat here to here is what we don't know. Your heat theta, you understand, where m equals to your mass, your c is equal to specific heat, and your theta is equal to the change in temperature, which is most of the times you express this as m c, change in t, that's theta 2 minus theta 1. So in this case we are representing theta 2 minus theta 1, or theta, as t. So here now what you're looking for is Cp to Cq, the specific capacity of P to specific capacity of what? Of Q. So from here now you notice that your C is equals to H over what? M theta. Okay, so your Cp will be equals to H P, which is H, over M MP, and then Tp. So here now, since we have a general equation, your Cp would just be equals to your Cp ratio Cq, which is equals to Cp over Cq, is equals to H over, we're told that the mass in P is twice, the temperature in P is twice that, and the mass is, so we have 2 m, the temperature is twice, okay, sorry, so we have that to be equals to 0.5 m times 2t. So this is divided by H all over m times t. So this is equals to H over 0.5, and this cancels it. So you have this mt, then this one goes off, you have mt all over what? All over H. That is your Cp over this. So this effectively cancels this. This is H, so this cancels this, and this cancels this. Okay, now so back to this. So your Cp ratio Cq will be equal to, this cancels this, so you have 1 ratio 1. This is 1. Okay, 1 ratio what? 1 ratio 1. Okay, so that is your answer, 1 ratio 1. So now question number 20. Question number 20 says, when the root mean square value of a source of electricity supply is given as 240 volts, it means that the peak value of the supply is what? So here you're given that the RMS, the root mean square, is 240 volts. That's given. Then the peak value is not known. So you know that your root mean square, RMS, is equals to the peak value over root 2. So therefore your peak value is equals to your RMS times root 2. This will be equals to 240 times root 2. Okay, so and your peak value will be equals to 340 volts. Okay, that's your question number 20.